Hi everyone. Now that we have talked about convolution and we know something about the Fourier transform, let's actually look at an example of how we use the Fourier transform to solve differential equations. And that's one of the major uses or applications of these transform methods, is not just to do things like specific engineering problems that have to do with frequency, but trying to attack differential equations with a method that goes beyond just guessing. Remember that differential equations are actually quite difficult to solve, especially if there's more than one variable involved. So in order to do that, we're going to need to record some basic facts that we've already seen for the most part. So recall, if I take the Fourier transform of a derivative of a function, then what I get is 2 pi is times the Fourier transform of the function. Okay, that's a very useful thing to have available because it means that if I have an expression that has derivatives in it, they all get replaced by just multiples of the Foia transform of the underived function. And that same rule holds for higher derivatives. So if I took the Foia transform of the nth derivative of f, then I just get more copies of 2 pi is piled on. But I still just have a Fourier transform of the original function f involved. So this is sort of the core idea of applying a Fourier transform to a differential equation. The second thing we need to talk about with Fourier transforms and differential equations is that the Fourier transforms of a lot of functions are just known things. We don't compute them by hand. We recognize them because they are from tables, or they have structures that we can look at and pull back over with a computer, and it will identify what function a particular transform came from. So that is not something that we're going to be computing by hand. A lot of this computation will be by hand, but then there's going to be places where we look at a function and say, I know that function is a transform of this function. And for the purposes of the first example that I'm going to walk through here, the one transform that I'm just going to assert is true, and you're going to have to keep in mind, is that the Fourier transform, so this is my assertion. This is a standard transform. And the use of a standard transform is part of the method of using the Fourier transform to study differential equations. So I assert the standard transform that the Fourier transform of 1/2 of e to the minus absolute value of t is equal to 1 over 1 plus 4 pi squared s squared. That's just a fact. If I see this, it is automatically the Fourier transform of that. And in the example we're going to write down, we're going to see that. So if we assume that we had this fact on a table, so this is a table fact, let's store that in the back of our mind, and let's look at applying the Fourier transform to the following differential equation. Suppose I just wrote down u prime prime minus u is equal to minus f. F of t is just some function. Now you've already seen this sort of equation on the left-hand side many times in your mathematical career so far. The way that you would have solved it in 244 was with the method of the characteristic equation, for example. But we're going to use what we're going to do is we're going to take this simple equation and use it to show how the method of using the Fourier transform works, to point to how this thing gets used in higher level applications. So what I want, is to find u of t. So I want an expression for u. At this point, I'm going to apply the Fourier transform to both sides of the equation. So I take the Fourier transform of u prime prime minus u is equal to the Fourier transform of minus f. Now, because the Fourier transform is linear, that means that immediately I can rewrite it like this. The Fourier transform of u prime prime minus the Fourier transform of u is equal to minus the Fourier transform of f. Now I can use the derivative rules to write down, well, this we can sort of think of as being the Fourier transform of the thing we're solving for. That's actually what we want. If we could find the Fourier transform of u, then we could find u by taking the inverse Fourier transform. So the game now is, can I isolate the Fourier transform of u? Because if I can, then I can apply f inverse to the Fourier transform of u, and that will give me the answer u. So that's what I want to do. So I'm going to apply the derivative formula to that term, and I'm going to get the following. 2 pi is squared times the Fourier transform of u minus the Fourier transform of u is equal to minus the Fourier transform of f. And that means that minus 4 pi squared s squared times the Fourier transform of u minus the Fourier transform of u is equal to minus the Fourier transform of f. And now I can isolate f of u because I can just factor it out. And if I do that, I'm going to get a Fourier transform of u times, well, I guess a negative Fourier transform of u times 1 plus 4 pi squared s squared is equal to the Fourier transform of f, negative. I'm going to get that the Fourier transform of u is equal to 1 over 1 plus 4 pi squared s squared times the Fourier transform of f. Okay, so this was the goal, was to try to get the Fourier transform of my answer all by itself. And on the other side, I've got this expression. So the key to getting back to u is to use the convolution theorem. If I could write this as the Fourier transform of some function g, then I could use the convolution theorem to write u as a convolution of f and g. So the game in questions like this is finding out what this thing is the Fourier transform of. Well, remember back at the beginning of our discussion, I wrote down that we were going to use the fact that 1 over 1 plus 4 pi squared s squared is the Fourier transform of 1/2 times e to the minus absolute value of t. So this is equal to the Fourier transform of 1/2 e to the minus absolute value of t times the Fourier transform of f. Now I've got one step left to go to figure out what u is. But remember that when I have a product of functions in the frequency domain and I come back to the time domain, what I'm going to get is a convolution of those functions in the time domain. So if the Fourier transform of u is equal to a product of Fourier transforms, then that means that u is equal to 1/2 times e to the minus absolute value of t convolved with f. So because the Fourier transform of u was a product of Fourier transforms, u itself must have been a convolution. So a product in one domain corresponds to a convolution in the other one. So a product in the frequency domain corresponds to a convolution in the time domain. And that's actually why we need the convolution theorem. If I want to use this to solve differential equations and I end up with a product of Fourier transforms, when I come back, I need to be able to write that down as a convolution to write the answer down. Well, that's it. This thing right here, this is the solution to the differential equation. If you wanted to write down exactly what it looks like, u of t is equal to 1/2 e to the minus absolute t convolved with f. And that means that you could write that as 1/2 times the integral from minus infinity to infinity of e to the minus absolute value of t minus x times f of x dx. And so this right here, this is your general solution to that differential equation. And notice that works for any f. I don't need to have special formulas to guess. This expression always solves that differential equation, no matter what f you put in. So despite the technical difficulty of having an integral equation involved in the answer, you should recognize that there's real power here because this is a single answer that solves every possible differential equation of the form u prime prime minus u is equal to minus f for any f. So let's look at an equation that is slightly harder, one that we've already come across. We did the differential equation for the distribution of heat when the heat was in a ring. What happens if we're not on a ring? So we're going to look at the heat equation. On the line, which means that we're talking about an infinite rod. So not the circle, but the line instead. And we're still going to give an initial condition for the heat equation. U of x and 0 is equal to f of x. This is the initial heat distribution. And notice that unlike the case on the ring, there is nothing periodic that we can take advantage of here. Now, the particular version of the heat equation that we're going to solve is the specific version, ut is equal to 1/2 of uxx. Remember, we can put that constant, we can make that constant anything we want by adjusting the units of the physical quantities we're dealing with. It turns out to be the case that with the 1/2 in place that you get a nice standard answer. And I'm following the way that Osgood has written this problem so that you can go to the book. If you're interested in this derivation, you can find it on page 177. And what I'm doing in class will track with what Osgood does in the text. Okay, so if I want to solve the heat equation, in this case with the Foia transform, what I want to do is I want to apply a Foia transform to both sides of the equation. But I have to pick a variable to apply the Foia transform with respect to, because the Foia transform takes in one variable and produces another. So what I'm going to do is I'm going to take a Foia transform with respect to x. Okay, and so I'm going to hit both sides with a Foia transform. And I'm thinking of f as being with respect to x. So on the right-hand side, I can use the derivative formula because I'm taking a Fourier transform of a second derivative, and that's going to be equal to 1/2 times 2 pi I s squared times the Fourier transform of u. That's just the derivative formula. On the left-hand side, I have to do something slightly different because I've got a Fourier transform with respect to x, but I'm feeding it a derivative with respect to t. So if I actually wrote down the definition of the Fourier transform, I would get this. This is going to be the integral from minus infinity to infinity of ut times e to the minus 2 pi I s x dx. Those variables are x in there because this is a Fourier transform with respect to x. This is the integral from minus infinity to infinity of d by dt of u times e to the minus 2 pi I s x dx. And that d by dt is a partial derivative because u is a function of x and t. But notice that the integral is with respect to x. There's nothing else in the integral that d by dt is interacting with. And so in a lot of cases, if the functions are nice enough, you can just switch the order of integration and differentiation. That has to be justified typically, but in this case, you can just assume that centuries of mathematicians and engineers and physicists have determined that in the case that we're talking about, that it's okay to reverse the order. And then this, that's just the Fourier transform of u. So this is d by dt of the Fourier transform of u is equal to minus 2 pi squared s squared times the Fourier transform of u. And now we have just an ordinary differential equation. This is a first order separable ordinary differential equation. And it's of the same form as something that looked like d by dt of y is equal to cy. And every equation of this form has a solution that looks like this. Y is equal to y of 0 times e to the ct. Because you divide both sides by y, you integrate, you're going to get t's and logs, you exponentiate both sides, and when you solve for the initial condition, this is the sort of general form solution that falls out of this. The same exact structure is present here. This is an ODE, it's first order and separable, and it's of this form, and so if you solve it, the solution that you get is the Fourier transform of u then must be equal to the Fourier transform of u at the initial condition times e raised to the minus 2 pi squared s squared t. We can go one step further with this simplification and remember that u of x and 0 is what we said our initial condition was. It's the initial distribution of heat on the line. So this is really the Fourier transform of u is equal to the Fourier transform of f times e to the minus 2 pi squared s squared t. At this point, following the model from the last equation, what we really hope is that this is the Fourier transform of something. Because if it was the Fourier transform of something, then I could use the convolution theorem to write down what u must be. Well, let's see. I consult my handy-dandy table. In this case, I'm consulting the Osgood text, and this is a standard Fourier transform. So it's not one that I expect anybody in here to have seen before, but recognize that things like this show up all the time as standard answers when you're doing Fourier transforms, and something that a computer is more than happy to tell you. So it turns out the case that g of x and t is equal to 1 over the square root of 2 pi t times e to the minus x squared over 2t. This function, if you Fourier transform it, you get that one. So the Fourier transform of g is equal to e to the minus 2 pi squared s squared t. Table, integral, totally common. Whenever you see an exponential and you think it's going to be a Fourier transform, it is. You just have to jiggle constants around to make it work. So, having carefully recognized with our deep well of knowledge about the tables of Fourier transforms that this is itself a Fourier transform, then that means that we can write down that the Fourier transform of u is equal to the Fourier transform of our initial condition f times the Fourier transform of the function 1 over the square root of 2 pi t e to the minus x squared over 2t. But now, since u, the Fourier transform of u, is the Fourier transform of a product, or is a product of Fourier transforms, then that must mean that u is the convolution of the functions. So because this is true, remember that's the goal step when we're solving these differential equations, is to write the Fourier transform of u as a product of Fourier transforms. Because as soon as I write that, I can use the convolution theorem to write u must be equal to f convolved with this thing. Or if you like, u of x and t is equal to the integral from minus infinity to infinity of 1 over 2 pi t square root e to the minus x minus y squared over 2t f of y dy. So u can be written as a convolution of these two functions. The dy is the integral, is the variable of integration here because we want the x's to survive the process of integrating. So this is it. This is the general solution to the heat equation on the line, as opposed to on a circle. And this thing right here, this thing is so important that it has its own name. So g of x and t is equal to 1 over the square root of 2 pi t e to the minus x squared over 2t is called a Green's function. And Green's functions are one of the core ideas that's used in the study of partial differential equations. So we can't really go any deeper than we've gone right now, but this is a launching point for the study of basically all systems that can be characterized with partial differential equations. I guess you could also call this a heat kernel. So the heat kernel somehow captures the fact that you're in the 1D rod case. This is somehow the intrinsic behavior of the rod. And then what you're saying is that the solution to the heat equation in the line is the convolution or the average of the initial conditions F and the basic intrinsic behavior of the line system. So this somehow captures the system, and this captures the initial conditions. And the solution then says that as time goes on, what you're doing is you're averaging. Remember, that's what a convolution does, is it averages things. You're averaging the initial conditions with the basic property of the system itself. So I wish we had time to go deeper than this, but this is the basic idea of how the Fourier transform is used, why convolution shows up, and how you can interpret a convolution as a mixture of something that describes the system that you're studying and the initial conditions blended together, which is what you would expect for heat spreading out on a line, is that the initial conditions are going to dictate something about it, but the initial conditions are going to be averaged, or the behavior of the initial conditions has to be averaged by the base behavior of the system itself. Okay, so the ideas that we presented here begin multiple other classes. If you're interested in this approach to differential equations and this transform methodology with the Foia series, you should take a look at partial differential equations, the math course, which picks up right here and develops a whole theory of general Fourier series that you can use, or the Fourier transform that you can use to attack partial differential equations that show up in all over science and engineering, all disciplines. The transform ideas that we came up with for solving differential equations in the ordinary case, well, we're sort of overkill with the Fourier transform. So the pivot that we're going to make from this approach, convolution and the Fourier transform, to solving differential equations, we're going to cut down and use a different transform to approach ordinary differential equations called the Laplace transform. The Laplace transform is only going to work on a simpler version of differential equations, but because we're going to make assumptions about the differential equations, that means we're going to be able to reduce the complexity of the transform that we need to study them. But the basic idea is going to be the same. We're going to use an integral transform to switch a differential equation into a different form, isolate the answer, and then use an inverse transform to come back just like we did here. This stuff is awesome. This really is the core part of this class that you're going to take away and be using in a lot of different areas, in aerodynamics, in heat, in gradients of all kinds, so concentration gradients. There's a million applications of this idea. And the fact that you can use the Fourier transform both to study the spectrum of a signal and also to find the function that satisfies some differential equation, it's quite a powerful mix of abilities that the Fourier transform has. So thematically what we did was we solved a differential equation like this. We had a differential equation, we transformed it. It became not a differential equation, but an algebraic equation, where we just isolate a variable, isolate f of u, and then we turned around and came back and solved the ordinary differential equation or partial differential equation by taking the inverse transform, which invariably involved the convolution theorem. All right. Million ships were launched from this idea. So we're going to change gears, but this is the culmination of our study of Fourier techniques. If you are interested in this, I very much encourage you to think about taking the partial differential equations class the next time it's offered, which is the next course in this sequence. And regardless of whether or not you see it in the mathematical context in partial differential equations, assuredly you're going to see it in your science and engineering applications coming out of this. All right, talk to you guys there.